Hi everyone. Today I'd like to talk through the factors that affect the ionization energies of the first 10 elements in the periodic table. I'll be discussing the factors of Z effective and electron shielding, and also introducing quantum mechanical exchange energy to explain some deviations from the general trends. I'm going to try to present this in a kind of casual way. If you like the style of this presentation, please give the video a like and consider subscribing to my channel. Okay, to start this discussion, I'm going to think about a hydrogen atom in the sort of general terms. A hydrogen atom, of course, consists of a proton as its nucleus and an electron. And this system is quite easy for us to think about because there's only really one interaction that's going on between these particles, and that's a force of electrostatic attraction between the nucleus and the orbiting electron. So one way we can think about this attraction is considering the electrostatic potential energy experienced by that electron around the proton. And also bearing in mind that the electron will always have some sort of kinetic energy. Now we might want to think about this as a total energy of that electron is equal to its kinetic energy added to its potential energy. And this would be a standard approach from any types of mechanics. And it turns out when we're talking about these subatomic particles, quantum mechanics has to be considered. And the major consequence of this is that the electron's total energy is quantized, as in it can only take discrete quantities. Now, I'm just going to quote the results from quantum mechanics for these energy levels for the hydrogen atom, and that is that the only possible total energies that are allowed are that the En, so for the nth energy level, the energies that are possible for an electron to have are minus the Rydberg constant times by Z, which is the nuclear charge squared, divided by n squared, where n is the principal quantum number of the energy level in question. This Rydberg constant is just an energy. So for example, if I measured it in electron volts, it's equal to 13.6 electron volts. So the important take home here is for hydrogen, where we're considering Z equals to 1 and the Rydberg constant is just a constant, the only possible energy levels are proportional to 1 over n squared. So if I were to plot these on a graph, the energy level there, we can see as n gets very large, we're going to tend to a value of 0. So there is always an upper limit on our energies, and all energy levels will be lower than this. So we can see that n equals 1 will be our lowest energy level. And for hydrogen, well, Z equals 1. So this energy level can be found at minus, well, just the Rydberg constant at this point, subbing in the numbers for Z and n equals 1. Subbing in n equals 2, we get the second energy level. The next one up in energy, n equals 2. And the energy of this level, well, subbing in the numbers, we've got Z equals 1 and n equals 2. So that's at an energy of minus a quarter times the Rydberg constant. And we can see these energy levels will keep bunching up towards the top. So n equals 3. This will be the third energy level, minus 1/9 of the Rydberg constant. And we'll keep on filling in and squeezing in extra energy levels up until the point where we get to the 0 of energy, which constitutes a time when the electron is no longer associated with the atom at all, as in this corresponds to the ionization energy of the atom. Now, we wouldn't be able to do very much science if we were just considering the hydrogen atom, the simple case where you just have a nucleus and one electron. There will be many occasions in chemistry where we've got multiple electrons in a system. So to take the next step from here, I'm going to consider the helium atom. And this atom is going to consist of a nucleus with a 2+ charge and 2 electrons around it. Now, there are still attractive forces for these electrons, but there's also a new interaction that can occur here, which is a repulsive force between the 2 electrons. Now, this situation is much more complicated to think about. It's a three-body problem, even just considering the classical kinetic energies and potential energies for the system. And it turns out there is a much more complicated quantum mechanical consideration we need to add in to be able to get an expression for a total energy. This is all connected to the Schrodinger equation, and I don't want to go into the details of that here, but we're just going to make some simplifications to try and help us think about this system when it gets a little bit more complicated. Now, one way that we can start to think about this is to try to think about one particular electron and its overall forces that are felt by it. So I'm going to consider the 2+ nucleus and one of the electrons sort of occupying a zone where the other electron can also try to exist. And I'll just highlight this other electron in red here. So the electron in red is being attracted by the nucleus, but also repelled by the other electron, which is nearby. And we can sort of vector average those forces. And the way that people do this to think about the overall attraction that that electron feels to the nucleus is to define a quantity called the effective nuclear charge, ZF, equals the nuclear charge, take away some sort of shielding constant. And I want to develop this idea through this video. If we can then define this electron to be in some sort of average field, we can then make an approximation that the energy levels of this system are just equal to, well, by analogy to what we had before, minus the Rydberg constant times by the effective nuclear charge squared over n squared. And this gets us quite a long way into thinking about the complications involved with multi-electron systems. And unfortunately, there is a quantum mechanical complication that we need to consider on top of this basic model as we move between the n equals 1, n equals 2, n equals 3 energy levels for these multi-electron systems. It turns out that they're not so simply just one energy level anymore. There are multiple orbitals that are associated with those, and they split into different energies at this point. And this is fine for the n equals 1 level. The n equals 1 level just stays as the same energy, and this is the 1s orbital, which you might be familiar with. Now for n equals 2, there are two possible orbitals. There's a 2s and a 2p. And it turns out that the 2p is higher in energy than the 2s. Now in the single electron system, the 2s and the 2p just have the same energy. But in this multi-electron system where there's shielding, there is a difference. Now to show where this comes from, we need to think about a concept called the radial distribution function that also comes out of quantum mechanics for these two different orbitals. Now for the 2s orbital, there is a node in its radial distribution function which looks something like this, whereas the 2p's radial distribution function looks something more like this. Now the fact that the 2s radial distribution function has this little humpy bit down here, we say that the 2s orbital penetrates the 2p orbital, by which we mean there's a fair amount of time when an electron is really quite close to the nucleus and therefore feels quite a lot of attraction towards it. We can have a look at our picture up here and we can imagine, well, if there's significant times when this red electron is really close to this one, the repulsion from the other electron isn't going to be as effective. So we'll feel an overall stronger force of attraction towards the nucleus, and therefore the energy level will be lower. And this is a key idea that extends to higher n orbitals, where we get more orbitals that lose their degeneracy on moving to the multi-electron system. But for now, I'm just going to focus on the first 10 elements. And so I'm only going to be considering the 1s, the 2s, and the 2p orbitals. So for the rest of this video, I want to have a think about the ionization energy. And the ionization energy is the energy required to remove an electron from its energy level so far away, so to infinity, such that it's no longer attracted to the nucleus. I can think about that as a final takeaway and initial state. So the ionization energy will be equal to, well, I can see my energy 0 on there, and that constitutes an n tends to infinity energy level. So I'm just going to call that E infinity. Take away, well, whichever energy level we happen to be in. So let's call it EJ. So I know by definition, the energy at n tends to infinity is equal to 0. So take away minus the Rydberg constant times by Z effective for the multi-electron systems divided by J squared. So this is just equal to the Rydberg constant squared, Z effective squared, divided by J squared, where J is the principal quantum number of the orbital that we're removing an electron from. So I need to quantify something about the shielding constant we defined above to help us define what the Z effective is for different atoms in the periodic table. And to do that, I'm going to use Slater's rules as an approximation, but quite a good one to gain some intuition. So within this video, I'm going to be using Slater's rules, but I won't be quoting them. So now just to get started, just to think about the helium atom, we have a nucleus of a +2 charge and an electron. And then what we're saying is that there's another electron in the environment of these two. So we're trying to consider how much this one overall is attracted to the nucleus. So using this model, the presence of this other electron in a 1s orbital introduces a shielding constant of 0.30. So essentially what we're saying here is the effective nuclear charge felt by the red electron is equal to, well, the nuclear charge, which is 2, take away the shielding constant, which is 0.30. And now we can have a look at some of the bigger atoms across the start of the periodic table. So just moving down to lithium, this one has Z equals 3, next element along. Now this has the electron configuration 1s2, 2s1 from quantum mechanics easily available energy levels. Now we have a slightly different situation here because any electron in the 2s orbital will be significantly further away from the nucleus on average than any electron that's in the 1s orbital. So in a very simplistic consideration, we might start to say, well, a 3 plus nucleus is there and it's got a couple of 1s electrons that are nearby, and then there's the final electron further out. Now, provided that further electron, the red one, is far enough away, we might want to consider this as a whole block of overall charge plus 1. But we know from the radial distribution functions that this electron here doesn't spend all of its time outside of that box. Some of the time, that electron is quite close to the nucleus instead. So on average, we define the shielding effects of these electrons. And because they're in an N shell that's one lower, each one of these shields by 0.85. So they're 85% effective at shielding that nuclear charge, not 100%. So this electron that's out here feels an effective nuclear charge of, well, the nuclear charge, which is 3, take away 2 times, well, 0.85. So that's the cancelling out of some of the nuclear charge by the other 1s electrons. So this is just equal to 3 take away 1.70, which is equal to 1.3. So now we can see as we move from helium to lithium, although there's been an increase in the nuclear charge, the outer electron is feeling much less of it and certainly not feeling the increase. So the outer electron in lithium feels much less of the nuclear attraction than the outer electron in helium does. Furthermore, the outer electron in lithium is in a 2s orbital, which is higher in energy than a 1s orbital. So combining this all together, we should expect it to be much easier to ionize, well, certainly remove the first electron from lithium than it would be to remove the first electron from helium. We can continue these ideas to think about the next element along, which is beryllium, Z equals 4. So this atom has the electron configuration 1s2, 2s2. So we can say that there's a nucleus of 4 plus charge with 2 electrons which are largely nearby, they're the 1s electrons, but there's 2 electrons in the outer shell, so the 2s orbital. So I'm just going to put one of them here in blue and focus on one electron as the electron of interest. Now, as before, those 1s electrons are quite close to the nucleus, so we'd expect them to be able to screen off about 85% of the nuclear charge. But that other 2s electron isn't so effective because it's not so close to the nucleus. It's spending a lot of time further away and not necessarily shielding the electron of interest circled in red. Now, electrons in this sort of type of environment are thought to shield somewhere in the order of 0.35, so 35% effective shielding. So to calculate the effective nuclear charge felt by the electron of interest, this circled one in red is equal to 4. Take away, well, 2 electrons, which are 85% effective at screening. Take away, well, one that's only 35% effective. Completing this sum, we'll get to a value of 1.95 as the effective nuclear charge for the outer electron of beryllium. So if we were to compare lithium to beryllium, the outer electron, the easiest one to ionize, in both cases, it will be an electron in a 2s orbital, so we can make a direct comparison here, and we can see that the effective nuclear charge felt by the electron in beryllium is much higher, therefore it will be much harder to ionize the beryllium's first electron. Therefore, we should see that in the data, which is measured experimentally. Hopping along to the next atom, which is boron, Z equals 5, which has the electron configuration 1s2, 2s2, 2p1. Now here we're getting to a situation where we have some electrons that are pretty decent at shielding that nuclear charge, namely these 1s, sometimes these are called core for that reason. But any electron in the same N shell, so either the s or the p orbitals, both of these are much less good at shielding the outer electron. So we'll use that 35% effectiveness figure again. So my electron of interest, the easiest one to remove, the one that's furthest out, would be this 2p. And the effective nuclear charge in this case will be equal to 5. Take away, well, there's 2 of the 85% effective 1s orbitals again. but this time there's 2 of the 35% effective 2s ones. So this will give me an effective nuclear charge of 2.60. Now we have to be a bit careful how we interpret this, because the energy of a 2p orbital is always higher than a 2s one. This is a quantum mechanical thing. So we've got two factors involved here. The Z effective has increased a little bit for boron, but also we're removing an electron from a higher energy orbital. So we might expect to see some anomalies in a plot of ionization energies with atomic number to account for this difference. And it turns out that the energy gap between the 2s and the 2p is sufficiently big that it actually becomes much easier to remove that electron from the boron, despite the fact that the effective nuclear charge has increased in a similar way than it did from lithium to beryllium. So going from beryllium to boron, we'd expect the ionization energy of boron to be a bit lower than maybe we might have expected. Now these are the next few electron configurations to get us up to element number 10, which is neon. And as we can see here, we're just filling up the 2p electrons. So this allows us to directly compare things here, because we'll always be removing from a 2p type orbital if we're trying to ionize the first electron. Now Slater's rules tell us that if you've got the 1s orbitals in all of these cases, the electrons in those orbitals are 85% effective at shielding, and any other 2s or 2p electron will be 35% effective at shielding, and that's due to the radial distribution function for those. So I'm going to take my outer electron as the electron of interest and work out how many electrons for each of these cases are shielding the nuclear charge. Note that the nuclear charge is still increasing as we go through this sequence. So here what I've done is kept in blue the electrons that are going to be shielding the electron of interest, which I've highlighted in red. So for boron, the shielding constant is equal to, well, 2 times those 85% effective shielding 1s electrons, plus 2 of the 2s electrons, which are only 35% effective. And this sums to 2.4. So this means, although there is a nuclear charge of plus 5, the electrons in the way are going to screen that charge by 2.4 units of elementary charge. And we can see as we move to carbon, all we're going to do here is add an extra 2p electron, which shields with 35% efficiency. So we have a sequence across these next 6 elements where we just add 0.35 to the shielding constant every time. And so we can compute all of the shielding constants for these atoms. And each one of these is going to be removing the electron from a 2p orbital. So we don't have the complications before of changing types of orbitals as well. So now we can compute the effective nuclear charge by taking the actual nuclear charge and subtracting the shielding constant. So for boron, that's going to be 5, take away 2.4, leaving us with an effective nuclear charge of 2.60. So the next one is carbon, has an actual nuclear charge of 6. So take away the shielding, which is 2.75. That will leave us with a residual effective nuclear charge of 3.25 for the outer electron. And I can just compute the rest of the values there in the same way. Now we can note for these 6 elements, this is just increasing in a sort of linear way as we go between these different elements. Now, because we're thinking about an electron in the same orbital for each of these 6 elements, we know that the energy level, or we defined it as En before, is proportional to minus Z effective squared. We also considered the ionization energy as a difference between this energy level and the n tends to infinity level. So the ionization energy will just be proportional to Z effective squared. Now that means if we were going to try to plot a graph of ionization energy against Z effective for these 6 elements, we might expect it to be something like this, like a curve, like a parabola. So the general trend will be increasing. Now, unfortunately, this is not quite what is experimentally observed. We see some other effects interfering with this general trend. So some of these elements are easier to ionize than others, and we need to look to quantum mechanics to see what's going on there. And to do this, I want to introduce a concept called quantum mechanical exchange energy, which helps us dig into more detail on the consequences of the electron configurations here that we've described. So this is a purely quantum mechanical effect, and we mustn't try to overthink this in terms of our general intuition. Where this comes about is far too much detail for this video, but I just want to quote the end results. Essentially, if two electrons are in degenerate orbitals, as in two orbitals that are the same energy and the same type, they will always prefer to align spin parallel. Now, if they do that for quantum mechanical reasons, it means they can't get very close to each other. There's almost like a void zone in between these two. And if you're interested, this is called a Fermi hole. So this will be going on in this set of 6 elements here where we're filling up the 2 p's. It means that we will always want to put electrons into these 2 p orbitals with as many parallel spins as possible. If we do that, we maximize the amount of separation that these electrons can get from each other, and we minimize the inter-electron repulsion. If we ever have a pair of parallel spins, they can get close. So we maximize terms to do with inter-electron repulsion. So this helps us explain why the electron configuration above, where the 2 spins are parallel, is better than the one below, where the electrons are paired up with opposite spins in the same orbital. Now this has some consequences when we're considering the ionization energy. So we need a way of quantifying this effect. The way this is done is to consider the interaction between the 2 electrons that are in the spin parallel state at the top. And we say for every pair of parallel spins, we get a K of exchange energy. And that's just a letter to represent the amount of energy associated with the benefit of having things spin parallel. So now I could put a third electron in that top one, for example. And in doing so, we gain not only an extra K from them being parallel there, we get a third exchange interaction there. So overall, we gain 3 exchange energy interactions, all of which lower the energy of that particular electronic state. So that means if we try to remove an electron from this system and go to a different state here, which only has 1 K of exchange energy due to numbers of parallel spins, there's actually a net loss in exchange energy of 2K. And overall, this means that it's harder to ionize. So on top of the generally increasing Z effective that we can see on this graph, certain electron configurations will be quite resistant to removing an electron from them, because doing so means that there are fewer Fermi holes and the inter-electron repulsion will increase. Now I have a graph here to have a look at some of the configurations for these particular elements and their exchange energy contributions. So here I've got the curve from before, which is purely down to Z effective and its impact on the ionization energy. So an ionization will constitute a mole of an element, call it M, losing an electron to form the ion in the gas phase plus an electron. So for that process, we might lose a favorable amount of exchange energy. And one of those cases in particular is for nitrogen. And we can see that here, where we're going from a state which started off with 3 Fermi holes, and so we quantify that as 3K of exchange energy, to a state that only has 1K, so therefore we lose 2K. So that's losing 2K's worth of stabilization. That means it's harder to ionize this. So this purple line here is to represent a 2K's worth of exchange energy to show that nitrogen is harder to ionize than we'd expect. Now just moving to the carbon. Well, in this ionization, it's a slightly different situation because we've only got 1 pair of parallel spins there. So the starting state has 1K of exchange energy, and we go to 0K. So therefore, there's a net change in 1K of exchange energy, and that means it's harder to ionize in general because the state was more stable at the start than we expected. So therefore, I'm just representing this purple line for carbon as 1K. Of course, for boron, we only had 1 p electron anyway, so there was no pairs of parallel spins in degenerate orbitals. So exchange energy doesn't factor into our consideration of ionization energy at all. Now, that is also going to be true for oxygen, which has the P4 configuration. When we ionize this one, we keep all the spin up parallel electrons, and the only one that we're removing is an electron here that doesn't have a friend to pair with in the same direction. So therefore, there is no change in K, and we get our ionization energy data point back onto our original green trend line due to the Z effective squared. But moving to fluorine and to neon, we get the same effect as before. We introduce an electron with a parallel spin to that fourth electron. So there will be an associated K of exchange energy loss for fluorine. And for the same reasons as for nitrogen, there'll be 2K for neon. And that's due to the fact that when we have that full outer shell configuration, we have a lot of exchange energy. We have 3K due to all of the ones that are pointing up, and we add on 3K for all the ones that are down. So in total, there's 6K. And in doing the ionization, will all the spin up ones, well, the exchange energy is going to stay the same, but the spin down ones, we've lost some exchange energy, and we go down to 4K overall for the end state once we've lost an electron from this system. Okay, so once we've embedded this quantum mechanical correction to our original curve, we actually get a trend that represents the experimental data for ionization energy that we have. And so we see this sort of jagged line going across. So generally a trend going upwards across these elements, but there's a jagged trend due to quantum mechanical effects, due to the configuration of the individual atoms in their ground states. Now, the ideas I've presented here will extend very well across the rest of the periodic table. This is just the first time where they might be important when we're considering trends, because there are 3 degenerate 2p orbitals. So these types of considerations will become super important when you're thinking about transition metals, for example, where you have 5 degenerate d orbitals, and also really important in the lanthanides and the actinides where you've got f orbitals. And the interplay of effective nuclear charge and exchange energy can explain much of the periodicity that we see across the periodic table, more so than just at the very top. Okay, I'm going to leave it there today. If you like this video, please give it a like and consider subscribing to my channel. Also, do let me know if you want me to talk about other topics in physical chemistry along these lines. Thank you very much.